Okay, so we're recording, and here's where we were last time. We were talking about oriented densities. I was kind of addressing this eyebrow-raising weirdness that happened when we were developing Stokes's curl theorem. Yeah, here we go. And we were looking at circulation density, and we found that the formula, well, I asserted that the formula for circulation density had this weird dependence on the surface in the form of the orientation unit normal vector being part of the formula, which is, it's just a little unexpected. Divergence being flux density, there's no normal vector there, nothing of the sort. Let's see, Green's operator, circulation density doesn't have anything to do with any orientation of anything. So anyway, this is a little, I'm going to say a little unexpected, but I started talking about how, well, maybe it's not really all that unexpected. After all, we have seen this happen before in the fundamental theorem of line integrals. Right, here's our fundamental theorem of line integrals, and if you look at the corresponding density, keep in mind we're computing change, so this is a change density. There is a dependence on the orientation. There it is, right? So, not our first time. So, how did we make ourselves sort of comfortable with this at that time? Well, I make the observation that really, even though this is arguably an integrand, it really makes more sense to lump these two factors together and call this the differential. After all, ds is describing the curve. But so is t, right? ds is describing the size of a little piece of the curve. T is describing the orientation of that little piece of curve. So the dx vector, being the combination of both of those factors, is everything you need to describe the little piece of curve. So again, it makes sense for them to be kind of lumped together. As such, then, let's look at this equation there and make an interpretation of this factor right there. That's not what you multiply by size to get quantity. It's not, right? But it is what you multiply, dot product, by what you could reasonably call oriented size, right, to get quantity. And oriented size is the term I use for the dx vector here because it is telling you two things. It is telling you the size by virtue of its magnitude, and it's telling you the orientation of that little piece of size by virtue of its direction. So in the same sense that this is oriented size, likewise, I think it makes sense to think of this, the gradient in this case, as being an oriented density. And with the quantity, accumulating quantity in question being change, I call this oriented change density. So we can take the same analysis with Stokes's theorem. Oh, and I got ahead of myself. I guess I've kind of already said this. This gradient, as an oriented density, is telling us two things. Kind of already said this, but let me say it again. By virtue of its magnitude, it's telling us how fast the function's changing. And by virtue of its direction, it's telling you in which direction is that change happening, right? The change is happening at this magnitude, being magnitude of the gradient, only if you're moving in the direction that you might want to call the uphill direction, right? If you're moving in a different direction, everything's different. Thus the dot product with the t vector. So anyway, two interpretations of the two different factors of the oriented density. Okay, same analysis works perfectly analogously for Stokes's theorem. Here is our first take on Stokes's theorem. We wrote this down. And as such, yes, you can interpret this as what you might call circulation density, in the sense that that's what you multiply by, I wanted a different color, what you multiply by size to get quantity of circulation this time. Okay. But again, kind of weird to have this as the differential and this as part of the integrand. Both of those factors are telling me about my little piece of surface. These make sense to be grouped together. grouped together there the ds vector, which we've already talked about. This ds vector is telling you two things. It's telling you the size of a little piece of surface that we're looking at, and it's telling you the orientation by way of the normal vector of this little piece of surface we're talking about. So with this interpreted as oriented size, likewise, and looking at this equation, this is equal to that. Likewise, this factor here, the curl, it's the thing that you multiply by oriented size to get quantity. That's why we would call it an oriented density. Right? Same motivation that we saw concerning the gradient vector and the fundamental theorem of line integrals above. It's kind of like a density in that you're multiplying by size to get quantity, but you're multiplying by an oriented size. So we're going to call it an oriented density. And again, it has the same sort of interpretations of the factors. This thing, if you break it down to its factors, the magnitude of it is telling you how much is this fluid rotating. To what extent is there a rotation? Total extent at a given point in this fluid, how much is that fluid sort of rotating? Right? And then it's also telling you, by way of its direction vector, it's telling you around what axis is this rotation. Again, how much rotation you're going to see depends on what direction you're looking in. Right? In the same way that how much change you will experience, you're not always going to experience the maximum change. You might not be walking uphill. Right? The u vector up here tells you what direction you have to go to actually realize the full change density. And likewise, this direction vector here tells you what direction you have to be, around which you have to be looking, around what axis do you have to be measuring circulation in order to realize the full circulation that this magnitude points to. All right, so picture, here we go. Here's the curl vector. And again, this tells you two things. The direction that it points, missed, tells you tells you what this axis is, that the rotation of the fluid, whatever that is, whatever the nature of the rotation of the fluid is, what is the axis around which the rotation is sort of maximally happening. It's kind of the analogous thing to gradient vectors. They point uphill. They point in the direction where you get the most change. Likewise, the curl points in the direction around which you get the most circulation. And the magnitude gives you a measure of kind of, in some sense, how strong of a twister, how strong of a tornado, how strong of a whirlpool, how much of a rotation is really happening. Okay. All right. Now, what I'd like to do now is to give you a little bit more geometric intuition for why it would make sense that the actual circulation density is a dot product here. Why should the normal vector matter, and why should it be a dot product with the normal vector? So, looking at just some examples. Now, these are just examples. This is not a proof of anything. This is intended just as a kind of a fleshing out, a couple of examples that track with the claims that I'm making about what curl does and what curl looks like. So, in this first example, we have a fluid that has an obvious sort of rotational aspect to it. I've drawn there. That's kind of rotating like this around that line. Okay, if I were to ask, to what extent does that cause a circulation around this boundary curve? Well, a lot, right? The direction that the fluid is rotating the direction that the boundary is kind of turning around in, the same direction, right? This fluid is moving right along with this curve. We would measure a lot of circulation here. So I'm going to say there's a lot of circulation around the boundary in this picture. Now, what does that have to do with dot product with the normal vector? Well, if we look at the curl, like so, right? And we look at the normal vector. These are the two things that we dot. Curl dot in is the dot product that is telling us, that's algebraically measuring for us how much circulation we expect. Notice there's a big dot product there too. And I pose this as a non-coincidental just feature of geometry, that when you have the fluid rotating around the same way that the boundary is rotating around the surface, right? If those line up, if the rotations line up, then the vectors perpendicular to them also kind of line up, right? So lots of circulation that we're measuring with the fluid going around the boundary lines up with lots of dot product between those two vectors. And now, by contrast, I mean, let's suppose that it's the other way. Let's suppose that there, instead of the fluid flowing along the boundary to a great extent as I have it there, what if same fluid? And what if my boundary, and let me get rid of the distractions up there. What if the boundary were just in a totally different plane? Just completely different. And I confirmed recently that I don't have the hand-eye coordination to do this at the same time. But if the fluid is going around like this, and if the boundary is going around like this, I'm not going to try it again, but if the boundary is going around kind of this way, and the fluid is going around kind of that way, they're not going in the same directions. There is this circulation that we're seeing in the fluid is just not happening along that boundary curve in different directions. And entirely consistently with the fact that there's really just not much circulation happening around that boundary, entirely consistently notice that the curl and the normal vector are also not really pointing in the same direction, right? They're perpendicular to each other as I have it drawn there. And this too, just intrinsic to geometry, the fact that the blue and green planes just kind of didn't line up. They're just totally different directions of planes. Likewise, the orange and purple vectors also not lining up. So this is, like I say, it's kind of a plausibility test, a plausibility argument. You would kind of expect, with this geometry in mind, that the extent to which these vectors, curl and in, the extent to which they either line up or don't line up, should coincide with the extent to which these planes either do or don't line up. So it's geometrically plausible that the dot product of the normal vector ought to matter. Okay, let me pause for a second, see if anyone has any questions on this. I hope that seems plausible. All right. Okay, so let's talk through some physical examples. One of these we've already talked about, this business about fluids in the plane. This is old news. We know that if we have a fluid in the plane, such as is represented by these arrows that I've drawn here, we have a vector field like that. And I like to think of this as being water kind of flowing along in two dimensions. And as y'all know, I like to imagine a little leaf, and that leaf is, of course, flowing downstream with the water, right? The water is what's telling the leaf what to do, so whatever the water's velocity is, that's going to be the leaf's velocity also. So that part's easy. The vector field is the leaf's velocity. But how is it rotating? What's the nature of the sort of the rotation of the leaf? Well, again, it's being pushed harder on that side, and it's being pushed much less hard on that side. And just kind of like if you're at the grocery store with a shopping cart, if you push only on the right side, you're going to take a left turn. Right? And analogously here, if you push harder on one side than the other, then in the net, you would expect there would be a rotational element. And the thing that measures this rotational aspect of the fluid is Green's operator. Right? Green's operator tells you how that leaf rotates. Okay, again, that's old news. That's chapter 6 stuff. I claim that it's very analogous to the following three-dimensional scenario. Again, suppose I have a fluid representing the velocity. Here I like to think of air instead of water. Three-dimensionally, I just find it a little bit, claustrophobic, thalassophobic, one of those, to imagine being surrounded entirely by water. I don't know, it just weirds me out. So let's imagine the fluid is air. There's air moving around because of the air conditioning or the wind or whatever. And imagine we have these little balloons that are floating, and they're just at that exact perfect stage where the net buoyancy and gravity cancels and makes them effectively weightless, and they'll just kind of go wherever the wind takes them. Right? So, again, the fluid, namely the air, is telling the balloon exactly what to do. So the velocity of the balloon is the velocity of the air. That part's very direct. The rotational aspect of the air is what's going to indicate the extent to which the balloon is also going to be rotating, in the same way that Green's operator was indicating the rotational aspect of the two-dimensional fluid. Curl is indicating the rotational aspect of the three-dimensional fluid, and therefore the nature of the rotations of these small little floating balloons. And so again, let's see here. I'll use purple. The direction that the curl points is an indicator of the axis that those balloons will be kind of rotating around. Those little balloons will be rotating, and the rotation will be around that axis indicated by the curl. The magnitude tells you in some sense how fast. Now, what are the units, and is it? Are there any other constants involved? Oh gosh, yes. It matters very much what the stickiness is between the air and the balloon, right? Is it rubber? Is it? Are there little? Is it like a shag carpet on the outside? Does it have fuzziness that's going to catch the air? That this matters, right? How much moment of inertia does the balloon have? Yeah, that matters too. Lots of things are going to matter. That's not our problem. What I'm asserting here is that the curl is one of the proportionality factors in deciding how much the balloons will be rotating. Okay, so longer curl vectors means more rotation. Shorter curl vectors means less rotation. Everybody buy it? All right. Okay, a little bit of an aside about physics. We're not going to spend a lot of time on this. This is more physicsy than the previous conversation that we had about electric fields and stuff. And it's more sort of a statement of empirical facts as opposed to intuitions about how to think about, I had this whole bit about thinking about gravity as communicated by tiny little particles that are being shot out of mass, and that this is what mass does in the same sense that light bulbs shoot photons, matter shoots gravitons. At least it's perfectly okay to think about it that way. Whether it's physically true or not, I don't know. That's somebody else's problem. But you can pretend that it does, and it will make all of the equations work out correctly. Okay, so this is a little bit more empirical, and I'm just going to make some statements, and you just have to take my word for it or follow up with physics. And here's my statement. If you have what we call a current field, which is a flow of charged particles, very often when you have a flow of charged particles, very often they're confined inside of a little copper wire, right? When you talk about current, typically we're talking about all the movement of the electrons is inside of that wire. Okay, but there's no reason that you have to confine our consideration to wires. We can have charged particles flowing every which way. They are, after all, little particles. We can think of them as flowing as a fluid. So that's all the current field is, just a vector field representing the flow of charged particles. And with that in mind, here is an empirical fact. Currents create magnetic fields. Don't ask why. This is empirical. You'd have to speak to whoever, if anyone created this physical world we live in, if you want to know why, right? We simply know that. This is, the way it works. This is all empirical. So, specifically, the flow is like this. Creates a flow like that. Some of y'all taken physics courses, right-hand rule, and all that business. So we have one vector field representing a flow of particles. It creates another vector field representing what we call the magnetic field. It just is. Okay, so now here's some more empirical, in other words, don't ask why, just facts of the matter, and that is that there is an observable relationship between current, this thing I here is called current, and magnetic circulation. Just, again, it is what it is, but current says how many of your charged particles are passing through a fixed surface per unit time. It's the total flow rate, if you will, of charged particles. Magnetic circulation is exactly what it sounds like. It's circulation, so vector line integral, of the magnetic field around the boundary of that surface through which you're measuring current. So now about these players, I can make a couple of observations. For one thing, easy point, circulation is exactly what Stokes' theorem computes. So I can just write down Stokes' theorem. There it is. Circulation, if you think about it, and now let's factor out that common factor there of mu naught. But this thing right here, sorry. This thing right here, current, charged particles per unit time passing through a surface, that's flux of the current field. If you think about it, this is in fact the very definition of flux. Given that you have a vector field representing the flow of a fluid, vector surface integrals are made for the purpose of measuring how much of that fluid per unit time is passing through that surface. So this is just kind of by definition in some sense. That's where that top equation comes from. Altogether, that you'll recognize the way I have all of this written. This is laid out on the page deliberately, similarly to where I wrote down some similar equations about Maxwell's first equation and some gravitational equations. I laid it out on exactly the same way on purpose. And the point here is that this version of what we call Maxwell's fourth equation and this version of what we call Maxwell's fourth equation, we call them the same equation because they say basically the same thing. One of these equations is just kind of the integral of the other, and the thing that connects them, the tool that relates the green version, what we call the integral version, to the blue differential version, is Stokes' theorem. So, if you've already taken an E&M course, this may conceivably connect some dots that you might not have previously been able to connect before, because after all, when you take a course like Physics 152, they don't assume that you've seen vector calculus, right? It's not a prerequisite of the course. They can't assume you know that. If you take E&M after this class, right, then I think you're going to find knowing Stokes' theorem, being able to make this connection in this way will connect a lot of dots for you that otherwise you might not have been able to connect. And one might even say this would give you somewhat of an unfair advantage over the other students. You know some of the underlying math that other students are just having to kind of trust. So anyway, I think this is a really neat observation. Okay, moving along. Okay, so another flashback. All of this is literally copy paste from chapter 6. We were talking about Green's operator and Green's theorem and all that stuff. We had this thing called a local test. Specifically, if you want to know, given a vector field, is it a gradient? The way you can resolve that question is just compute Green's operator and ask, is it equal to 0 or is it not equal to 0? Very handy, right? This global feature of there being a single function whose gradient it gives the vector field everywhere. That's what I call a global statement, right? Is arbitrated by what I'm going to call a local question. You just have to compute Green's operator individually, one point at a time, and if every individual point gives Green's operator equal to 0, local test measuring each point independently, then you get this global result of there being a single function, a single anti-gradient for that vector field. Okay, now where did this conclusion come from? Well, we made the observation that, path independence simultaneous with vector fields being a gradient. Path independence can also be rephrased in this other way over here, right? All three of these statements inside of the green, we've already talked about why those are equivalent. And then I made the observation that, these two statements here are easily related to each other. These two statements, if you have some function whose double integrals are all 0 for every domain, no matter which domain you look at, double integrals always 0. The only way is if that integrand is itself 0. Okay, so what's the connection between the green statements and the blue statements? The connection is the fact that closed line integrals are what we compute with Green's theorem. Closed line integrals are double integrals of Green's operator. So that connects the green to the blue. That's what then establishes that these two top statements are equivalent, and therefore what establishes that you can use Green's operator as a local test for a vector field being a gradient. Okay, now again, I did that quickly because this is old stuff. We talked about this back in chapter 6, but I wanted to remind you what the structure of the argument was, because we're going to do the exact same thing now in 3 dimensions. I kind of waved my hands at this back in chapter 6. I made a vague reference to not really yet having the necessary theorem that we would need to fill in the blanks. But the argument's the same, and we now have the proper tools. These 3 things are simultaneous for all the same reasons. If you have a vector field whose flux is 0 through every surface, the flux is always 0, then that vector field has to be 0. And the connection between these two groups of statements this time is the fact that closed line integrals can be computed with Stokes' theorem in 3 dimensions as fluxes of the curl. So it's not the same as Green's theorem. In Green's theorem, we get closed line integrals are double integrals of Green's operator. This is an intrinsically 2-dimensional statement. It only works in 2 dimensions. The analogous thing in 3 dimensions is Stokes' theorem, and so different test results. Our test for path independence then our test for conservativeness, if you want to use that language, is whether the curl is equal to 0. Everybody see how these are morally equivalent arguments? It's really very, very similar arguments, just slightly different tools for slightly different contexts. Okay. All right. Okay. We've already seen examples of this test in action. We did that back in chapter 6, so I won't do other examples now. Okay, so now here's another sort of analogy that I want to set up. By the way, a lot of books on multivariable calculus don't include this discussion I'm about to show you. I think that's a major oversight. What I'm about to show you is a powerful computational tool. As you can see, I'm already making a reference here to path independence. You can see the title of this is surface independence. You can probably guess where this is going, at least somewhat. And let me recognize that I've already kind of observed that path independence, look, I mean, any time you could use path independence. You could also use the fundamental theorem of line integrals. Most of the time, the fundamental theorem of line integrals is pretty good, so from a computational point of view, path independence has, rare moments of utility, but most of the time it's just kind of the not quite as useful method as the fundamental theorem. Not so with surface independence. Surface independence is awesome in ways that path independence is not. And the details of that will flesh out over the rest of this week. So first of all, real quick, let me remind you what path independence is before I extend to surfaces. Recall that if we have two curves, C1 and C2, with the same boundary, that means that they start at the same point, they end at the same point. Two curves with the same boundary. And I add, same boundary with the same orientations, in the sense that it's not good enough for one to start where the other one ends and to end where the other one starts. No. They have to start at the same point. Period. And then they also have to end at the same point. Also period. Okay. If that's the case, let's consider the green line integral over C1 and the blue line integral over C2. There are some special vector fields called path-independent vector fields for which these two line integrals are always the same, no matter which curve C1 and C2 that you pick, with the understanding, of course, that yes, they have to start and end at the same points. In other words, they have to share the same boundary. Okay, so path independence, natural term, because of course what it's saying is that the value of the integral doesn't depend on the path. So, great terminology. Real quick reminder here. Color coding. Alternative phrasing of path independence is that all closed line integrals are 0. Another way to say that is that if you have two line integrals being equal, that means that their difference is 0, and their difference, of course, is the integral along the boundary of the whatever region that they between the two of them they bound. Okay, so I hope all of this on path independence is familiar. So we're going to extend this now by increasing the dimension. Dimension is going to go up by 1. So instead of talking about curves, one-dimensional curves, we're going to talk about two-dimensional surfaces. Instead of talking about what you might call zero-dimensional boundary points for curves, we're going to talk about the one-dimensional boundary curves of surfaces, etc. So everything's going to go up by 1 dimension. And here's what it looks like. Suppose you have a surface, S1, and another surface, S2, that have the same boundary. Now, keep in mind, S1 and S2 are surfaces. the boundary of a surface is a curve. So when I say S1 and S2 have the same boundary, I mean they have the same boundary curve here. Like that. So, said differently, it's like S1 and S2. Imagine my left hand is S1 and my right hand is S2. Having the same boundary means that they have to kind of glue together along their boundaries. In other words, it's like this, and it's like I'm, I've got a bug in my, I've got captured a bug between my hands here. It's I've enclosed a space, a region of space in between my two hands. Okay. Everybody all right with the picture? In this scenario, two surfaces, same boundary curve. There are some special vector fields that are what we call surface independent. And what that means is that the green flux and the blue flux are the same. Said differently, that the value of these fluxes is independent of the surface. And of course, independent of the surface, thus the term surface independence. How are we doing so far? Is everybody with me? Questions? I emphasize, I'm not claiming yet that there are any vector fields that have this property, and I think it's worth sort of emphasizing. It kind of doesn't seem like, it seems like this is an unrealistic request. Wait a minute, you're telling me that there are vector fields where you can kind of pick whatever surface you want? You always get the same flux? For totally different surfaces, just so long as they have the same boundary curve. But totally different surfaces seems implausible. Then again, path independence seemed implausible, and we found out that there was a bunch of vector fields that were path independent. Okay. All right. Now, let me talk a little bit about orientation. Reminder, these two boundaries, S1's boundary and S2's boundary do have to be the same, and furthermore, they have to be the same with the same orientation. They have to be the same as oriented curves. That means, so for example, let's suppose, as I've got it drawn here, that the boundary is oriented that way. Then the orientations on these surfaces kind of have to go like this. The S2 orientation has to, I've got my greens and my blues backwards. Oh, man. All right, I better fix that. Sorry. Real quick fix. S2 is the green one. S1 is the blue one. My bad. Okay, there we go. So S2's orientation would kind of have to be upward in order to, thumb, fingers, swirl, side swipes, and all that to get this orientation on the boundary. And then S1's boundary would also have to be upward. Now, morally equivalent reason, again, you have to have induce the same orientation on that shared boundary. Everybody okay? Now, this temptation to look at these two orientations of these two surfaces and say, hey, whoa. One's inward, one's outward. That seems inconsistent. On the other hand, they are both upward. That seems consistent. So which is it? Are these the same? Are they opposite? I want to point out they're actually neither. These two orientations, N1 and N2, are on different surfaces. You can only compare orientations, right? There are only two orientation options on a given single surface. These are different surfaces. There is no comparison between them. So don't make the mistake of viewing these as either being the same or as being opposite. They're, loosely speaking, somewhat the same in the sense that they give the same orientation on their shared boundary. They are somewhat loosely speaking opposite in the sense that as part of the boundary of the solid, one's plus and one's minus. Namely, one is outward and one is inward. So they're kind of the same in a way. They're kind of opposite in a way. They're actually neither. Right? But anyway, just make sure that you don't sort of get yourself confused by conflating these two different senses of of interpretation. Let me point out that we actually had the same scenario here. All right, you look at these two curves. Are these two curves oriented the same? Well, kind of the same in the sense that they start at the same place, they end at the same place. They're both oriented, you might say, to the right. Okay. But as part of the boundary of this D region, one of them is oriented counterclockwise, the other is oriented clockwise. So again, kind of the same, kind of opposite, depending on your point of view. Don't get bogged down in accidentally conflating those different points of view. You want to think carefully about whether you're interested in their shared boundary or in how they participate as part of the boundary of something else. And likewise here. Right? These two surfaces, as drawn, have the same induced orientation on their shared boundary. They have opposite signs in how they are part of the boundary of something else, how they're the boundary of that solid R there. Okay, very confusing point. All right, that said, oriented as they are, notice that I can think of them as part of the boundary of this whole thing. Let's see here. I have this whole thing here, and as part of that boundary of R, one of them gets a plus, one of them gets a minus, and then a rephrase that we can make of surface independence is that the closed flux is 0. Everybody all right? Okay, now, this is what surface independence should be. Again, I have given you no reason to believe that there is any such vector field. But if there were a vector field that we would call surface independent, this is what it would kind of morally have to be. This is the surface equivalent of path independence. So are there any actually surface independent vector fields? And yeah, it turns out there's actually a bunch of them. And that is curls. Curls are all surface independent. Here's why. Let's think about the green flux integral. How would I compute the green flux integral? Well, the vector field is a curl. A flux of a curl is a circulation. Circulation of the anti-curl, G. How would I compute the blue flux? Well, I would compute that blue flux, again, with Stokes' curl theorem. After all, I'm looking at a flux of a curl. Fluxes of curls by Stokes' theorem are circulations of the anti-curl. Both of these computations are done over the corresponding boundaries, which of course are the same boundary curve. Therefore, both of these computations are they're computed by the exact same circulation integral, and therefore these things are the same, and that means that our vector field is surface independent. So, what a wonderful little, convenient little argument. Very nice. Everybody okay with that? Anybody have any questions? So every curl is surface independent. If you find yourself needing to compute a flux of a vector field, which is is a curl of something, the vector field is surface independent. You can change your surface however you want to. It's a very powerful computational tool. Okay, now I do want to show you one more thing, then I'll give you an example. That is the local test. Now, everything we've got down here is kind of new, but these three statements are all the same. We've kind of talked through the sameness of these. Surface independence can be written multiple ways. One of the ways to express surface independence is that closed fluxes are all 0. So we know those are the same. And I just asserted above that every curl is surface independent. Actually, I kind of proved that. And then I asserted without proof that every surface independent field is also a curl. And that proof is actually quite hard. It's beyond what we can do in this course. But also true. So we're just gonna state that. Okay, so again, 3 kind of analogously true facts. Here is a familiar statement. If you have a function whose triple integrals are all 0, how could that be? What? You got a function, the triple integral is 0 for every domain, no matter what domain you look at, always triple integral 0, no matter what? What function could that possibly be? Only the 0 function. So we find ourselves in this familiar situation. We've seen this layout of statements before. What's the connection between them? The connection between them is the theorem that relates closed fluxes to triple integrals of divergence, aka Gauss's theorem. So the divergence theorem is the thing that connects left to right. Therefore, that is puts in the final piece of the puzzle that shows why it is that we can use divergence as a test of whether or not a vector field is a curl, or more importantly, whether or not a vector field is surface independent. Okay, pausing. Questions? Everybody all right on that? Okay. Example. Now, everything that I did on the previous page I know was kind of abstract and kind of proofy. Right? This is a rubber meets the road example of how extremely powerful this idea of surface independence is. Suppose I want to compute this flux right here. Vector field given, surface given, how would I compute this flux? I guess you could brute force it. It's going to turn out to be pretty hard. As it turns out, the final double integral that you get is it's done over an ellipse, which is going to have square roots inside. There's going to already be a significant polynomial as part of the, from the vector field and the capital N vector. This is going to get hairy and unappealing. Okay. Now, one thing you could do. Well, let me not get ahead of myself. So how are we going to compute this flux? I'm going to first take this vector field. I'm going to compute its divergence. Why compute the divergence? I'm going to come back and talk about that in a few minutes. Or maybe more likely tomorrow. But this theorem right here kind of gives it away. If I compute the divergence and if I get 0, then boom, I know I have a surface independent vector field. That gives me lots of options. That opens a lot of doors and could be really useful. So, okay, let's compute the divergence. It's easily computed to be 0. So I do know that I have surface independence. I also know that my vector field is a curl of something. And I've got options. Now, before I go on, is everybody with me so far? Computed divergence. I've established I've got options. Now let me try to explain why surface independent is so important. Oh yeah, go ahead.
Yeah, if divergence is 0, can you automatically say that it's 1 path independent and 2 is the curl of something?
It is surface independent. Yes, and it is the curl of something.
Okay.
Yeah. Now, so you touch on the first thing I was going to say. Hey, if this is a curl of something, if my vector field is a curl, why don't I just find the anti-curl and I can compute the flux of curl just as a line integral of my anti-curl? Why wouldn't I just do that? That's what Stokes' theorem says. Why not go for it? And here's why. You may recall, I've never showed you how to compute an anti-curl. There's a really good reason that I have not shown you how to compute an anti-curl. It's really hard. There kind of isn't really a simple little sort of, easy to remember algorithm for finding an anti-curl. It's just hard. So yes, you could, in theory, use Stokes' theorem to relate this to a line integral of anti-curl. But we can't find the anti-curl, so it's kind of moot. So let me remind you, why did I kind of diss on path independence as a computational tool? Well, because I just used the anti-gradient and fundamental thermal line integrals, and bam, you got it. We had a better option when we were entertaining what to do with path independence. here in this context, I don't have a better option. I don't know how to find anti-curls. Stokes' theorem is kind of moot in a way because I don't know what to do with it. So now surface independence is our only real remaining option. And so here's the big idea. My original surface was this. Whoops. Stylus. My original surface was this. Its boundary is that. I am allowed to use, because of surface independence, I am allowed to say phooey on this surface. I don't like this surface anymore. It's all curvy and stuff. I can pick any other surface that I like that has the same boundary. And I propose that when you have the choice, most of the time, pick a flat surface if you can. Now, of course, that requires that the boundary be, in a flat plane that would allow it to be the boundary of a flat surface. But if you can, and this is, pick the flat surface. Why not? So, phooey on the blue surface. We replace it with this new green surface, and I don't even need that blue anymore. I'm just going to get rid of that. And on this green surface, the calculation turns out to be very convenient. You notice the normal vector has got a lot of zeros in it. Most of the algebra just disappears by a dot product with mostly zeros, and you end up with an integral that also very conveniently, zero by symmetry, and we're done. No elliptical bounds with square roots in them, and ugly polynomials and integration by parts and trig substitutions and other nightmares that we don't want to have to deal with. So surface independence was a massive victory in this case. Everybody happy? Let me warn you about one thing. Please do think carefully about the orientations. Maybe I'll say a few words about this next time, but we do need to worry about the orientations and how this normal vector implies this normal vector by way of them both having to have a shared orientation on their boundary. Y'all have a good one. See you later. See you on Friday. Make sure, of course, that I mark you down for